ماذا لو أن الكفاءات الجزائرية من كافة أنحاء العالم تجتمع معا؟ ماذا لو أن هذه الأدمغة بمختلف تخصصاتها تتكاثف لتطوير التعليم والبحث العلمي للنهوض بالجزائر في مختلف المجالات؟ هل تعتقد أن هذا مستحيل؟ أبداً، فالحلم يتحول إلى حقيقة من خلال الشبكة العالمية للعلماء الجزائريين إيناس. رغم أن إيناس هي مؤسسة غير ربحية وتعتمد فقط على تبرعات الأفراد، إلا أنها استطاعت أن تبني جسورا من التعاون وتبادل الخبرات بين أبناء وطننا الحبيب من الداخل ومن مختلف بلدان العالم، ساعية لصقل المهارات واحتواء المواهب وتبادل الخبرات وإيصال التجارب النافعة لخدمة الوطن.
السلام عليكم ورحمة الله وبركاته. مرحبا بكم معنا في لقاء جديد للشبكة العالمية للعلماء الجزائريين إيناس. معكم محمد عمروش. I am the project leader of the Earthquake Hazard Mitigation Project. In this project, we try to invite experts in earthquake engineering and geophysics in a monthly manner in order to share the seismic hazard awareness and science in general. And this month, we are very pleased and honored to have another keynote speaker, Ustad Dr. Zaid from USA, who kindly accepted to share with us his expertise. Assalamu alaikum, Ustad Muhammad.
وعليكم السلام ورحمة الله وبركاته. أنا سعيد جدا أن أنا بشارك معكم النهارده.
شكرا جزيلا على تقبلك لدعوتنا. So I will briefly introduce our guest speaker this month. Dr. Zaid is the Vice President of Engineering at Dynamic Isolation System, DIS, in USA. He finished his bachelor and master degree in structural engineering from Ain Shams University in Cairo in Egypt. And he was awarded his PhD degree from the University of Nevada, Reno in 2016. In 2022, ENR Southwest named Dr. Muhammad among the top young professionals under 40 of age. And Dr. Muhammad is specialized in earthquake engineering and has designed earthquake protective systems for more than 100 building and bridges projects. And this month, he's going to share with us seismic-based isolation technology, conception and implementation. It is a topic. It's a hot topic. It was highly asked from audience to introduce this topic. And this month, we finally succeeded to have one expert to share with us his expertise. تفضل, Dr. Muhammad, the floor is yours.
Thank you very much. Today I will be talking about seismic-based isolation in general, like protective systems. How can we protect our buildings, bridges, structures in general against earthquakes? I will begin with the outline of the presentation. The first two topics that I'll be talking about. I will start with seismic isolation in general. What's the concept and what are the benefits of using seismic isolation? And then I will show some structural damages from previous earthquakes. When you design a building or a bridge conventionally without using a protective system, what's the damage that you will be expecting? And I will show some pictures and some photos from actual earthquakes. And then the third point will be the main topic of my presentation. I will be talking about the main product that it's used for seismic isolation. And this main product named is lead rubber bearings, or Lrbs. I'll be talking about the components of the lead rubber bearings. I'll be talking about testing, what are the benefits, advantages of the bearings. I will show also a case study for cost saving. How can you save money when you use lead rubber bearings when you are designing a bridge? And then I will I will show different projects and different applications from different countries around the world, from Chile, Peru, the US, Japan, different buildings, bridges, all kinds of applications. And also I'll show that it's good for either new constructions or retrofits. And after this point, I will show some actual examples from isolated structures around the world that passed through major earthquakes and they had no damage. And then I will end this point number 3, showing some research projects. Like we also work with universities. We have lots of research projects with universities using the lead rubber bearings as well. And then after I finish this part, I will show another product. It's also for seismic isolation, but it's a little bit different. We call it low mass isolation or equipment isolation. In summary, sometimes we want to protect a very expensive equipment that we have. We want to protect a very expensive, say, computer or a piece of art. So sometimes the building itself is not isolated, but we need to isolate something small. So we produced, or we have invented a product that can protect equipment. And then if we have some time, I will also go to show some damping products, not only isolation. One of the most important damping products that it's mainly used in Japan, and it's now introduced outside of Japan, and it's named viscous wall dampers. So I'll begin with the first topic, which is the concept and benefits of seismic isolation. I will begin with a short video to show you the difference between two buildings. One of them is fixed, and the other one uses seismic base isolation at the base. So this is a shake table. This is a shake table testing showing the differences between two buildings. As you can see, when I shake the two buildings, the first one, which is fixed, you can see all the forces and deformations from the earthquake is transferred to the building itself. You can see that it's moving very strongly. But when you look at this building, which is seismically isolated, you can see that all the deformation goes to the bearings themselves, and the building feels almost no forces, or sees no forces and no deformations. So this is the main concept of seismic isolation. The main concept is to decouple the building from the ground. You have to decouple the building from the earthquake. So all the deformation will go to the product that you are using, and the building will not feel anything. If it's fixed to the ground, all the forces and all the deformations will go up to the building and will cause damage. To translate this video into some technical knowledge or technical information, this is the typical response spectrum that we get from an earthquake. Acceleration versus period in seconds. Let's assume that this is the period of a non-isolated structure. So around 1 second is the period of the non-isolated structure. What does this mean? It means that a non-isolated structure will move in an earthquake one full cycle in 1 second. So it's moving very quickly. So the period of the non-isolated structure is 1 second. So it's moving very quickly, one full cycle in 1 second. So what's the main idea of isolation? The main idea of isolation is to lengthen this period, is to make the building move slowly. So usually for isolated structures, the period will be around, say, 3 seconds, just as an example. So the period now, the building now is moving slowly, which caused reduction in forces in the building itself. So, and this is the main concept, is to decouple the structure from the ground and introduce a plane of lateral flexibility, something very flexible. You put it under the building and will lengthen the period. And as soon as you lengthen the period, as you see, the forces are much less. So the forces between this point and this point could be 3 to 5 times less. And not only this, so we do period shifting, but also these products add damping to the building itself. So we decouple the structure from the ground, and we also absorb the energy of the earthquake by adding additional damping. So what's this photo on the top right? This is an actual photo of a hospital that was built in Colombia. So the owner of this hospital was about to open the hospital and to start operations in 2004. And in 2004 in Colombia, it was hit by a very strong earthquake. And as you can see, the building was damaged. The owner spent 3 years to retrofit the building in order to be operational again. And since then, he learned his lesson, and this owner decided to use seismic base isolation in all his future projects. So as soon as he tried, he learned his lesson the hard way. He was hit by the earthquake. He stopped operations for 3 years. Then he decided to use isolation since then. Now in the next slide, I'll start showing some damages for buildings and bridges from previous earthquakes. And I will begin with a very popular earthquake that happened in New Zealand in 2011, Christchurch earthquake. And I'm showing 2 photos here. These photos are for Christchurch downtown, before the earthquake and after the earthquake. As you can see, after the earthquake, most of the buildings, like 70% of the buildings in the downtowns, were demolished. Okay, is this good? Is this bad? Let's think. So per the structural engineers, this was okay because there was no collapses or minimum collapses, so they satisfied the codes. So all the structural engineers were happy. Minimum collapses, life safety was achieved, but the owners and the public, they did not know this, so they thought that their buildings are earthquake proof, so they were not happy. So there was like a debate back there in New Zealand: who is paying for the insurance, who is paying for all this demolition, who is paying for retrofits? So that's why it shows that the conventional designs, yes, they are good, life safety is achieved, but they are not good enough, because you will lose functionality, you will lose the continuous functionality of your building. You will need either to demolish the building and build a new one, or repair and retrofit your building, and might take 1 to 2 years to make it back to work. Another example, also from New Zealand, the Kaikoura earthquake in 2016. And this one is showing a bridge example. These are some damages from bridges during the Kaikoura earthquake. And this is the source. There is a paper published in 2016 about this earthquake, showing different damages that happened to all the bridges there. And this shows the damage that happened to this bridge. It's the same case as the previous case. This is the perfect damage for structural engineers. So when they see this, it's a perfect plastic hinge. Everyone is happy, all the engineers are happy. There is no collapse. So everything was good. But for the functionality of the bridge, it has to be closed and it has to be retrofitted or repaired for a long time before they can open it back to public. Another very strong example from 2010, an earthquake in Chile. It was a magnitude 8.8 earthquake, and this earthquake caused lots of damages and collapses actually in Chile. More than 300 bridges were damaged during this earthquake. And since then, since 2010, seismic isolation was introduced into Chile. They started having lots of projects in Chile, lots of bridge projects, lots of hospitals and buildings. So they also learned their lesson the hard way. An earthquake, a big earthquake hit the country, lots of collapses, lots of damages, and then they started to use isolation. Another also example that affected actually the economy of a whole country, which is the Wellington earthquake. It's also in New Zealand. These are some photos from the Wellington container port. So it was damaged significantly during this earthquake. And because of this earthquake, this port was closed for 1 year, for almost 1 year, so that they can do the repair. This affected the economy of the country. All the ships and all the containers that were supposed to go to this port, they had to change the route and go to another port, and affected the whole economy of the country. So these are just some examples showing you that conventional designs, they are good, they satisfy the code, life safety is achieved. However, they are not good enough because your building or your structure will not be functional after the earthquake. Now I will go to the third topic, which is the product itself. What do we use to protect this building? What's the seismic isolation product? And as I said, the product that I will be presenting today is, the name of the product is lead rubber bearings. And this is the most common product or seismic isolation product that it's used worldwide. This is how the product looks like. This is the lead rubber bearing, or LRB. What are the main components of these bearings? Internally, there are layers of rubber vulcanized to layers of steel shims. So many layers of rubber and many thin layers of steel shims. They are vulcanized together. In the middle, there is a lead core. And the function of this lead core is to dissipate and absorb the energy of the earthquake. From outside, there is a cover rubber. And the function of this cover rubber is to protect all the internal components of the bearing. This cover rubber is made of specific types of rubber that has high environmental protection properties that can protect all the internal components of the bearing itself. And then finally, we have mounting plates. One will be in the bottom and one will be on the top, so that we can connect this bearing to the substructure and superstructure. If you look at the components of this bearing, you will notice that vertically, as I said, there are layers of steel and layers of rubber. So vertically, this bearing is very stiff, very, very strong. It can hold the weight of the building and the bridge. So it's very stiff vertically, but laterally, when the earthquake comes, it's very flexible so that it allows the bearing to move and absorb all the energy of the earthquake. So vertically, it can carry loads up to 4,000 tons or 5,000 tons. It's very strong, but laterally, it's very flexible so that when the earthquake comes, it will decouple the building or the structure from the earthquake. In our company, we have built or manufactured lots of bearings, more than like 27,000 bearings around the world. So very small bearings and very big bearings. The diameters ranges from 150 millimeters to more than 1.5 meters. The lead core diameters are also, we have done also very big lead cores up to 400 millimeters, these internal lead cores. And as I said, the vertical capacity is very high. It could reach up to 4,400 tons. And this is an actual photo from one of the sites in Turkey for the bearing. And as you can see, the lower part is already connected to the substructure, and the top part will be connected to the superstructure with anchors. This bearing is still under installation. One of the projects that we have finished in Turkey. The bearing is connected with anchors up and also anchors down to the concrete. So these bearings, when we design them, what about testing? How can we make sure that these bearings are good? Most of the codes around the world, they require to test these bearings, all of them, 100%. So if a project has 100 bearings, so we test 100% of these bearings. Some of the European codes do not ask to or ask for testing only for, say, 20% or 30%, and this is also acceptable in some of the codes. But usually, as part of our quality control, I always prefer to test 100% of the bearings to make sure that every single bearing is good, because this bearing is affecting the lives of people, affecting the structures. So we test 100% of these bearings. And in this slide, I'm showing you some actual videos for testing. As you can see, the bearing is tested with high speed. There is axial load on this bearing. The bearing moves. This bearing was tested to half a meter, about 480 and the diameter of this bearing is 1 meter. As you can see, it's very, very flexible laterally, and vertically, it's holding the load of the building itself. Another example for another testing. This was a project in California, in the US, where the peer reviewer asked to push the bearings even more during testing to make sure that they are good. So the diameter of the bearing was 45 inches, and it was pushed to 45 inches of displacement. It was stretched very strong. And as you can see, it's very robust. It will just come back to its original position. Another very recent test that we finished this year for a big project in New Zealand. As you can see, the bearing will be stretched about 800 millimeters. It's a huge bearing for a big bridge in New Zealand. And as you can see, it's stretched very, very strongly. So when the earthquake comes, the bearings will move, the building or the bridge will not feel anything, and then the whole thing will recenter and come back to its original position. And these bearings do not need to be replaced. They will just come back to their original position and will be ready for the next earthquake or for the aftershocks. You don't need to replace them after the earthquake. So what are the advantages of using LRBs or lead rubber bearings? There are lots of advantages. One of the main one is the durability. You want to put these bearings under a building or a bridge and keep them there for the rest of the life of the structure, for 50 years or 70 years. So the durability of these bearings is very strong. As you can see in these photos, some of these bearings are, you can see the concrete is split on the bearings. You can see under a bridge, there is moisture, there is contamination, there is dust. These bearings can, they are very good and they are not affected by the moisture or contamination at all. So there is a stable long-term performance. So they will stay for the rest of the life of the bridge or the building, and also the properties will not change. They might change very minimum, but the properties will are stable for the rest of the life of the building itself. Some other photos showing the durability of these bearings. This is a photo from a wharf in Tacoma that we have done about 2 or 3 years ago. As you can see, these bearings, they are very close to the water. They're not just very close, they are actually submerged in water twice a day. So the water will go up and down, and nothing is wrong with the bearings. The properties remains the same, and the life of the bearings is the same as the structure itself. This is also another bridge in Azerbaijan. The bearings are very close to the water, so they are in the splash zone. And because of the cover rubber that I mentioned before, all the internal components of the bearings are protected. Another advantage of this bearing is the cost saving specifically when you use it for bridges. And I'm showing now an actual case study for an actual bridge that was constructed in Mexico. It's a Mexicali bridge. And this study was done by an engineering firm named Cowten for this bridge. What did they do? They actually designed the bridge twice. They did an isolated design, and then they did a conventional design. And then they compared the sizes and the volumes of the materials that will be used. As you can see, for the conventional design, let's take an example. For the columns, the concrete volume ratio, it's 1.56 to compare to the isolation. 2.85 the steel volume ratio. So the volume of the material for the conventional design was much higher, because the forces, the lateral forces that are coming from the earthquake from the conventional design is much higher than the isolated case. And if we translate all these numbers into money, they found that even the price of the isolator was about $1 million, but at the end of the day, the total difference in project between the conventional design and isolated design was about $2.8 million. So there was a lot of cost savings also when they used LRBs in the bridge. So this is also one of the most important advantages when you use LRBs with bridges specifically. After I spoke a little bit about the product itself, show you the testing, now I will show you different projects and different applications around the world. We have done lots of projects in more than 22 or 25 countries around the world. In all the countries that has earthquakes, you will see lead rubber bearings or seismic isolation. I will begin first with new buildings. This is one of the most common application. You have a new building that you want to build. You want this building to be functional after the earthquake, so you will go and ask to be seismically isolated. This first photo is for a residential building in Japan. And this photo proves or shows the difference in the public awareness between Japan and other countries. In Japan, the public and the awareness of the public is very high. They know about seismic isolation. The regular people in the country, they know about seismic isolation. They know about earthquakes. They have all this knowledge about isolation and earthquakes. So when a regular guy wants to buy an apartment, he will ask the owner, is your building isolated or no? And then if the building is not isolated, then he might say, no, I want an isolated building. I want to protect my savings. So the public there, the awareness is very high. So that's why you'll find lots of residential buildings in Japan are isolated. And this is not the case for many of the other countries outside. Even here in the US, the awareness is not like Japan. So you will see that most of the residential buildings are not I can say 100% of the residential buildings in the US are not isolated, just because of the difference in the public awareness. If you go to South America or Latin America, you will find that they have frequent earthquakes. Since 2010, 2011, 2012, they have an earthquake every day. That's why the awareness of seismic isolation also in South America is very high now. You will find lots of universities and lots of businesses that ask for seismic isolation. And these are some examples. This is a university in Peru they wanted the university to be functional after the earthquake, so they used lead rubber bearings. And this is a car dealer in Chile. Some other examples for new buildings. This is a museum in Japan. So the owner wants to protect all the expensive artwork that they have inside the museum. So they decided to isolate it so that after the earthquake, no damages will happen for the internal parts of the building itself. Taiwan, a hospital. Tanzhou Hospital, back then when we were building this hospital, it was one of the biggest seismic isolation buildings in the world. And as you can see, if you look at here, you'll see that some of the locations you can see 4 bearings are used. Some of the locations we are using only 1 bearings, but because this hospital was huge and the loads were very high, we had to use more than bearing at the same location. So it was one of the biggest buildings, isolated buildings in the world. More case studies and more examples, but now I will move from new buildings to bridges. Bridges also is a very good example for seismic isolation. This is an example from Turkey. This is a highway, 400-kilometer highway with many bridges, and they used more than 2,000 lead rubber bearings to isolate all the bridges along the highway. It was a very critical highway for the country, so they want this highway to be functional after the earthquakes, so that all the cars and ambulances can keep functioning. So they used more than 22,000 isolators for the bridges. Another example from Colombia showing different structural systems. Colombia, Peru, showing some arch bridges. Also, you can use isolation. So isolation can be used for regular bridges, typical designs, or for also different structural systems. Another bridge examples, but this time from the US, the Coronado Bridge in South California. This bridge is actually crossing a fault, crossing an earthquake fault, and the seismic demand is very high. So in order for them to retrofit or repair or to strengthen this bridge, it was easier for them to use isolation instead of going down the water and increasing the sizes of all the foundation. So it was easier for them to use isolation to reduce the forces and saved lots of money of doing lots of work underwater. This is also the Golden Gate Bridge, the northern approach of the north approach of the Golden Gate Bridge. It was also isolated by lead rubber bearings. Another application is sky bridges or pedestrian bridges. You can use isolation for a bridge between buildings. This is the Twitter Sky Bridge in California, in San Francisco. Another bridge in Mexico that also uses isolation to make sure that it's functional after the earthquake. Talking about countries that did not use isolation before. This project is in Nicaragua. It was the first isolated project in Nicaragua. It was under construction last year, but they opened this bridge very soon or very recently. We as a company, we helped the engineers and we helped the company to do, and we helped the government to do all the designs and approvals. And we went to the country. We have seen the installation. We made sure that everything is good, and the government and all the engineers there were very happy to have the first isolated bridge in the country. Another application, also bridges, but not roadway bridges. We can also isolate railway bridges. It's not easy, it's a little bit difficult, but it's also doable. This is the JFK Airport light rail. It was also isolated with lead rubber bearings. It's a big viaduct around the airport that makes the movement around the airport easier. When they used isolation, they did a lot of cost saving for the substructure, and they also had lots of cost savings due to less of the relocation of the services. So the services under the ground, they had now less foundations, so the relocation for the services was much easier, so they had lots of cost savings, and of course accelerated construction time. These are just showing applications, buildings and bridges. Let's go now to another application, which is the retrofit. You have a building, an existing building that it's old, and you need to retrofit it. This is very popular application for buildings with a very nice architecture. So these are old buildings. They were built, say, 100 years ago or 150 years ago, but now with the current seismic codes, they are not good. So they have to do something. They have to strengthen these buildings. But at the same time, they don't want to change the architecture. They don't want to put big braces in the facade. They don't want to put lots of structural steel members that will ruin the architecture of the building. So the best solution here is to use seismic isolation. You will just go there, cut the building, cut the columns from down, push the building up, put the isolations, and put the building down. You will keep the same architecture because you have reduced the forces significantly that are going up to the building, and the building will look like this, exactly the same as before. This is not cheap. This is expensive, but the clients that have buildings like this and they want to keep the architecture of the building, they are willing to pay more money to keep the buildings look nice like these ones. And these are also some other examples for the retrofits. This is the Asian Art Museum in San Francisco. They also wanted to keep the same architecture, so they used seismic isolation. And this is another project also in California, the China Basin. This has a nice story behind it. So the client or the owner, they built 3 stories in the very beginning, no isolation. And then after 5 or 6 years, they decided to add 2 more stories. But when they did the calculations, they found that because of these 2 stories, lots of forces, lots of earthquake forces will go down to the building, down the lower part of the building. So they need to do a lots of retrofits and a lots of repairs for this building. So the owner decided to use seismic isolation, but not here in the base. They used isolation here, as you see. It's a mid-level isolation. So all the forces that are coming now to the lower part of the building is less than if it was fixed to the building itself. So the client or the owner was able to do minimum strengthening for the building by using isolation. This is one of the most I always like the retrofits. They are very, very strong projects. Going to a different application, which is the hospital. And this is the most common application around the world because hospitals, they are very critical, very important. They have to be functional after the earthquake. Even if there are some damages in the buildings, in the houses, people has to find a hospital to go to after the earthquake. So many hospitals now around the world are isolated. And we at DIS, we have isolated more than 60 hospitals in 8 countries. This is in Taiwan, this is in the US, and this is in Turkey. Even in some of the countries now, like Peru, like in Turkey, the law is forcing the hospitals to be isolated. It's by law. The hospital has to be functional after the earthquake. This is the most critical location that has to be functional after the earthquake. Turkey and Peru, the law is forcing everyone, either public hospitals or private hospitals, to be earthquake protected. More applications and more examples. The wharves. This is an example for Broadway Pier in San Diego. It was also designed twice, a conventional design and an isolated design. And the engineer was comparing the differences also in prices and the difference in materials. The diameters of the piles without bearings was about 54 inches, huge piles, 36 inches with isolation. And the total cost of the project, if it's not isolated, was $4 million, and it was $2.8 million if it was isolated. So to retrofit or to repair or to strengthen the pier, they decided to go with isolation. And this is also another example for a new wharf that I mentioned before, the one in Tacoma. It's in Washington State in the US. They also used isolation to make sure that the port is functional after the earthquake. I'm trying to show different applications and different projects from around the world so that I just open the eyes that it's not just used for building or a bridge. It can be used for all different applications. What else? A very important application is the data center. And this is an example for a data center in Chile. This data center was designed to be tier 4. Tier 4 means that the downtime for this data center cannot exceed 8 minutes per year. So this is the downtime. It has to be 99.995% functional through the whole year. In order for the owner to achieve these 8 minutes and to achieve the tier 4, this building has to be isolated so that after the earthquake, they have only the 8 minutes and they have to be functional and back to business again. So the data center is also a very popular application for seismic isolation. Another application that we have done in Russia, an offshore platform, was also isolated. Another application in Japan, it's very also interesting application. This is a dam in Japan, and this is the control building that controls the gates. So this control building has all the equipment and all the machines that controls all the gates for the dam. So this building was isolated. So the owner or the government, they wanted to make sure that after the earthquake, this building is okay, no damage to the building, so that someone can go inside and control the gates. We might need to open the gate or close the gate after a big earthquake to control the waves behind the dam. Another very interesting application in California. This is an Indian temple. This is the architecture of the temple. It's exactly the same as in India. So the objective was to have the same architecture in India, the same as in California. But California is very seismic. How can I keep this? If I just put this on the ground and an earthquake comes, it will just fall down. So they used isolation in order to reduce all the forces that are going to the temple and keep the architecture of the temple itself. So the previous slides, I was showing applications and different projects. In this slide, I'm showing actual isolated projects that passed through actual earthquakes, major earthquakes, and they were functional with no damage after the earthquake. This is a bridge in California that passed through an earthquake in 1989. This is a bridge in Mexico, the Mexicali Bridge, and it passed through the 2010 Mexicali earthquake, and it was just functional after the earthquake right away. And this is a hospital. I have another slide talking about this hospital. This is the USC Hospital in Southern California. It was isolated, and it passed through the 1994 Northridge earthquake. I'll talk in the next slide about this hospital a little bit. And all these other buildings, they are in Japan, and they passed through the 2011 Tohoku earthquake, and they are all isolated, and they are all just functional after the earthquake. Going to the next slide to talk a little bit about the USC Hospital. This hospital or this case study is very interesting. So this hospital was built in the 90s, and it was isolated with lead rubber bearings. The hospital was instrumented on all the stories. They had accelerometers that can measure the acceleration of the earthquake. So the 1994 Northridge earthquake hit the hospital. And then after this, the hospital was absolutely functional after the earthquake, but we wanted to measure what are the forces along the building itself. So when we looked on the ground, the earthquake, the forces was about 0.37 G. The PGA was 0.37 G. But when you look along the building itself, all the instruments or all the accelerometers measured around 0.13 G up to 0.11 G. So the forces were reduced significantly from the ground below the isolation level up to the top of the isolation level, and nothing happened to the hospital. Another hospital that was very close to the USC hospital, its name is Olivier Hospital, and it was also instrumented, but it was not isolated. And when they measured all the forces along the building, so at this location, the ground was 0.8 G, and all the forces were magnified until the top of the building, it was about 2.3 G. So the forces were very high at the top of the building. So there is amplification if you are fixed to the ground, as I showed in my initial video, and there is reduction in forces if you are using isolation, because all the deformation already went to the isolation themselves. Let's go to the next slide, and I'll talk a little bit about some of the research projects that we also do. It's not just practical applications, we also do lots of work with the universities. This is a shake table test for a full bridge. It's a full curved bridge that was done at the University of Nevada, Reno. In this university, they have 4 shake tables. On each shake table, there was an abutment, and then a pier and another abutment, and a full bridge on the tables. And the whole table, or the 4 tables, were moving together. And this is the video showing how they are moving. Here is the isolation. The whole bridge is shaking and then recenters and goes back. And here is a zoom in. As you can see, the whole thing is moving, and after the earthquake, the bearing will recenter and return every back to its original position. Another video from the same project, and this was also part of the research. The professor back then decided to push the bearings and the bridge even more. They decided to push the bridge 300% more than the capacity of the bearing itself. So this is a zoom in on one of the bearings, and it was pushed significantly beyond its capacity. Here's the bearing. You can see it was stretched significantly and then return back and recenters again. And I want you to notice something. See this black spot in here? This was not there before the test. The whole bridge sat down on the bearing. Let's look at this again. See, the whole bridge was stretched significantly, and then the bearings are robust. The whole system returned back to its original position and recentered. This shows also one of the biggest advantages of these lead rubber bearings. They're very robust. They can recenter and come back. So this is the first product, or the main product, which is the lead rubber bearing. I showed some testing, some applications, examples, actual earthquakes. And now I will move to the next product. And as I mentioned in the very beginning, sometimes we do not need to isolate the whole building or the whole bridge. Sometimes I have something small inside my building that it's very expensive, and I need to isolate this specific part of equipment or this specific computer, for example. And we call this product low mass isolation. Sometimes we call it equipment isolation or non-structural isolation. It's not like a structural like the bridge or the building. And this product was developed by our company, and there is a patent on this product itself. This video will show the main components of this product. So it's mainly composed of some steel frames, very simple angles, connected to springs, and these springs connected to some cables to the ground, and the whole thing stands on wheels or casters. So it will move during the earthquake and recenters and comes back. Let's look again. So a steel frame, simple angles, springs connected to the ground with cables, moves on wheels. The whole thing will move during the earthquake and will recenter because of the spring and comes back to its original position. It's very simple, very easy, and you can use it for simple equipment like this. And this is just some cross sections from the system itself, showing how it looks like. In this picture, this is like the zero displacement position. Here is the spring connected through bushings to the ground. When you push this way, the spring will be extended. This is what will happen. And when you push this way, the spring will be extended. And after the earthquake, the whole thing will recenter because of the force of the spring. Let's look at some videos as well to understand more how does this work. So in this video, I'm showing 2 tests on shake tables as well. This is an isolated server on the platform, and this is a non-isolated server. It's fixed to the table. You will see when I start shaking both servers, what's the effect of the earthquake on these servers. Let's compare. As you can see on the isolated one, the server is just moving parallel to itself. Nothing is happening. If you look at this one, all the cables are unplugged. The whole thing wants to fall down. Although this earthquake is actually 50% than this one. So in isolation, the whole thing is moving very, very smooth. No forces are moved to the server itself. But in this one, you can see everything is unplugged. The whole thing wants to fall down. And this is the difference between isolated platforms or isolated servers and non-isolated. Let's look at some applications and some examples and some actual projects that were finished. These are some photos that were taken from the Salt Lake City public safety building. They had some servers inside the building that they wanted to protect. So they used the platform or the isolation platform that we developed underneath these servers to keep functional after the earthquake. Another very interesting example is for a platform that we finished with the Department of Defense here in the US. So they had some equipment that are very, very critical. This equipment or these servers, they control the satellites in space. So in order for them to control these satellites and to be functional after the earthquake, they needed some isolation system like the one that I showed you in the very beginning. And as you can see, you can have different configuration of the isolation system itself. It could be just a small part, as I showed in my video, or it could be a full floor or a big platform like this, so that you can put lots of servers on the same platform. Another also very interesting example. This is in Berkeley, Lawrence Berkeley National Lab. They have computers that controls the grid, the electricity grid in the US. The value of these computers is like $100 million. So they are very expensive. They need to keep them after the earthquake. They have to be functional after the earthquake. They are controlling the electricity of the US. So they decided to isolate the whole floor of the building. So these are all the computers, and this is the isolation system. The whole floor was isolated, and this blue part is we call it the moat or the gap, because when you do isolation, you need some space to move, as I showed you in the videos. So when the earthquake comes, this blue part will break and allows the whole floor to move, so that all the computers will be functional after the earthquake. So even if there is damage in the building itself, the computers will continue to be functional. Another application, and it's also very interesting, especially I think now in the Middle East, because we have lots of very expensive artwork and monuments. So this is an artwork in California. The cost or the value of this statue is about $700,000 or $800,000, and it's very slim and very tall. So if this statue is fixed to the ground, as soon as the earthquake comes, the whole thing will just fall down and break. So they decided also to use the seismic isolation platform, which will just move back and forth, and nothing will happen to the statue itself. Another product that was also developed, it's a 3D equipment isolation. So in this one, we are not only isolating horizontally, we are also isolating vertically, because sometimes the earthquakes or the vertical component of the earthquake is very high. So we added some other vertical components, like some dampers, some springs, so that you can also isolate the equipment vertically, not just horizontally. And this is a short video showing how it works. See, the whole thing is moving horizontally and also vertically. So the equipment is protected from horizontal earthquakes and also from the vertical component of the earthquake. This is just a brief about this product and about seismic isolation in general. I will talk a little bit about another product, which is damping product. It's not seismic isolation. It's a viscous wall damper. What's a viscous wall damper? This is a schematic of the viscous wall damper. It's composed of mainly of a steel tank, and this steel tank is filled with a viscous fluid with very high viscosity, and then there is this vein, like with a T-section, that goes through the viscous fluid, and then when the earthquake comes, the whole thing will move back and forth, and the vein will shear into the viscous fluid and absorb the energy of the earthquake. To explain this more, I have a short video here. We have a tank that is connected to the lower part or the lower beam of the building. And then we have a vein that goes into the tank connected to the top floor. So when the earthquake comes, the vein will shear the fluid and absorbs the energy of the earthquake. And that's why we call it viscous wall dampers. It's a viscous wall. It's hidden inside the wall of the building. What's the history behind the viscous wall dampers? These walls were developed in Japan in the late 80s. The first project in Japan was in 1993. Since then, they had more than 100 projects in Japan using the viscous walls. It was introduced to the US in the early 2000s. Between 2014 to 2019, we worked in a big hospital project in the US, and this was the first viscous wall damper project in the United States. And then we worked on another residential project in Mexico in 2018. So in North America, we had only these two projects, and we are working on a third project now. And I'm only showing these two projects now because one of them was a new construction and one of them was a retrofit, also to show that it can be used for both. So let's look at the Mexico project first. So this is a residential building in Mexico. The owner of this building, they finished this construction back in 2006, but because of some financial issues, they did not finish the building. And they came back in 2017 and they wanted to finish. But in 2017, they found that the seismic hazard has increased and this building is no longer good. It cannot sustain the actual hazards now. So they decided to use viscous wall dampers to absorb the energy of the earthquake coming and have minimum strengthening to the building itself. So they used viscous walls along the building, along the height of the building. If I go to the next project, which is the hospital that I mentioned in the US, the name of this hospital is CPMC. It's in San Francisco. This hospital is very close to the San Andreas Fault. It's just 11 kilometers. So they needed a protection system or a protective system to protect the hospital after the earthquake. And as you can see, these are some photos for the walls along the height of the hospital itself during construction. These are also some photos from the hospital. You can see along the height of the building. And the good thing, or one of the biggest benefits of these walls, is that they are not under pressure. There is no high pressure involved. So there is no seals, there is no leaks, and minimum maintenance, minimum to almost no maintenance. Also, there is a huge benefit, which is the architectural flexibility. The architect of this hospital decided to go with the walls because they will be hidden within the walls of the building itself. They can have windows here because these are hospitals, they need windows. If they decided to use bracings, they will have big diagonals that is crossing the windows and crossing the walls. So that's why they decided to go with the walls, because it offers lots of architectural flexibility. In order to see the performance of these walls, we have done lots of prototype testing at the University of California, San Diego. We tested 5 dampers with sinusoidal testing and actual earthquake testing. We also did 2,500 cycle for wind displacements for tests, and over 25 tests that we have done all over, and the performance was totally stable. And this is a video of the test. It's a shake table as well. and this is the final loop that you will get, the final force displacement loop that you will get out of this test. Before I finish, I also want to say that we, as I mentioned before, we don't only work in practice. We also do a lots of research with universities. We publish a lots of papers. I personally have published lots of papers. These are just some samples. I have a paper that it's talking about the difference between seismic isolation in South and North America. I have lots of case studies for bridges. This paper was presented in New Zealand. I have also another paper that talks about the wall dampers that I just mentioned. And finally, in summary, I want to say that seismic base isolation and energy dissipation devices, they protect lives, they protect structures, they protect money, contents, and they ensure the continuous functionality of the structure after the earthquake. They are 100% effective. They are widely used. They have been used since the 1970s. They are not a new technology anymore. Many of the engineers consider this as new technology, but this is not the case. They have been used out there for a very long time. And now they are also affordable. They are not very expensive as before. Thank you very much for listening. And I'm open for any questions.
Thank you. Thank you very much, Dr. Muhammad. Jazakallah khair. Thank you for the very insightful presentation. It was fantastic. I mean, this is really what I was expecting, actually, to cover basics from the conception of the base isolation, demystifying the technology, and then giving some very insightful, very interesting case studies and examples all around the world, how this technology can help us to save our building lifelines and protect our patrimony, historical structures. So thank you again. Thank you very much for your presentation.
You're welcome.
So I would like to thank our audience and remind our audience that we can take questions, and you can ask your questions in the comment sections. I can see we have a lot of questions and comments in the section as I was expecting, because this is a really hot topic. So let me pick some questions from our audience, if you don't mind.
Okay.
So first question from Facebook is, what are the disadvantages of LRB in comparison to triple friction pendulum?
Okay, so there are two main products that are used for seismic isolation. I mentioned one of them, which is the LRB. And then we have friction pendulums in general, whether they are single friction pendulums, double or triple. Both products are good. Both products have some advantages and some have advantages over the other. The only or the main advantage of the pendulums over the LRBs is that they can, the pendulums can extend the period more. They can go to 5 seconds. But this comes with a huge cost, because when you go to 5 seconds, the displacement is huge. So you are losing lots of area of the building itself. And this can be sometimes very expensive, because you have a huge moat now, could be 1 meter or even more. So this is one of the disadvantages, or I can call the advantages of the pendulums over the LRBs. But one of the main advantages of the LRBs over the pendulums is the durability, as I mentioned. The pendulums, I have seen lots of pendulums in different countries. They are friction materials, and friction will be affected quickly with the environmental conditions. If they are not protected or sealed properly, you can see under bridges, the water and the contamination and everything can go inside the pendulum, and the performance will change with time. And I have seen lots of cases like this, either in the US or outside of the US.
Thank you. Thank you very much for your response. I'll take another question from Facebook. Thank you very much for the presentation. How would you estimate price for an RC building retrofitting using base isolator? And is there any post-implementation maintenance required?
Okay. So for the retrofits, it's, as I mentioned, it will be very expensive, and it will be case by case. And it's expensive not because of the price of the isolators itself. It will be expensive because of the whole process of cutting the columns and pushing the whole, or jacking the whole building up and putting the LRBs. So this one is case by case, depends on the size of the building. So I cannot say a price for this. I can say for new buildings that isolation will add to the cost of the building between 1 to 5% for new buildings. This is well known, but retrofits, it's very difficult to give because it's case by case. And for maintenance, so usually the LRBs, they are maintenance free. But after the earthquake, people or the engineer has to go there and will look at, do inspection for the building itself, and will also have to do some inspection for the bearings. They have to make sure that the moats are free. There is no rocks like fell down into the moats and preventing the building from moving. So it's not like a maintenance, it's just some inspection and just to be careful. And if something wrong, or if say an earthquake that came that was bigger than the design earthquake, and one of the bearing doesn't look good, then what will happen is that this bearing will be replaced, similar to the retrofit process. You'll just put a jack, lift this specific location and put the bearing back. But during the, as I mentioned, the LRBs have been used since the 70s. I haven't seen a single case that this happened actually. So during all the earthquakes that I have seen, the whole thing returned back and all the bearings are good.
Thank you very much for your response. I will take another question from our audience. We know that short buildings are affected by acceleration, and most high-rise buildings having more than 1 second period are affected by velocity. And since the velocity is triggered by the friction ratio C, so isolation is the best solution for high-rise building. Is this concept always true? I mean, can we use isolation for all type of building considering their cost?
So isolation is more applicable for more the fixed and rigid buildings, not the tall buildings. When the building is becoming more and more tall, like the period is say 2 or 3 seconds, so the concept of isolation is already achieved, because the isolation will move the period from 1 to about 3 seconds. So if the period of the building is already 3 seconds, for example, it's better to use dampers, not isolation, so that you can control these movements of the building itself. So for tall buildings, tall and flexible buildings, it's better to use dampers than isolation. If the building is tall and rigid, like it's like they have braces or shear walls and the period is still around the 1 second, yes, we can use isolation. And we have used isolation for some buildings in Japan, because in Japan, the construction is not like the US. It's very heavy, very big columns. I remember around 35-story building in Japan. It's very tall, so I'm expecting the period to be long. But the construction is different. They're using braces, very big shear walls, so it was very stiff, so we were able to use isolation. So if the period of the structure is around 1 second, use isolation to extend it to 3 seconds. If the period is already 3 seconds, it's better to use dampers.
Thank you very much. We'll pick another question. What are the technical criteria for resorting to the use of seismic isolation, and are there examples for existing buildings? Thanks. I don't know if I understand the question. What do we mean by technical criteria? But I don't know. Well, personally, I didn't really understand what we mean by technical criteria. Maybe some comments about some regulations or laws on the criteria of implementation of that seismic isolation. Yeah,
so there are lots of codes. Like I will assume that they're asking about the technical criteria, like the codes. The ASE 716 and the ASE 722. There is a chapter 17 is talking about seismic isolation, and chapter 18 is talking about damping. And there is also the ASH2 for bridges. The ASH2, there is a guide specifications just for seismic isolation, just talking about isolation. And there are also the European codes. They have isolation sections. In Peru, in Chile, in New Zealand, now they are developing their codes. I have seen a code in New Zealand that I saw the draft. I think it's coming now very soon to public. Peru, they have a code now also that it's controlling the design.
Okay, thank you very much. We will take, I think, one last question. We have so many other questions and comments. Does the location of the VWDs affect their efficiency in a matter of structure behavior? Since in the photos we haven't seen any symmetric localization in the facades.
Yes. So what happened specifically in the photos in this hospital? So this hospital was a steel moment frame, so the drifts were high, and they wanted to put walls to reduce the drifts. So it was a basic trial and error. So what will happen is that the engineer will start in the model, say in ETABS or SAP, will put walls along the height, and then we'll see the performance. is this the required performance that he's looking for or not, and then he will start eliminating some of the walls and see what's the performance until he reaches the best performance that he needs. But usually we need more walls in the bottom, and then they get less as we go up. But it might be just random, as you have seen in the photos, to reduce the price and to have the best performance.
Thank you very much for your response, Dr. Mohammed. So again, everybody is thanking you for the very insightful presentation. In the comments, we have a lot of thank messages from YouTube and as well as Facebook. So before closing, I have one personal question, and then we can close this webinar. Have you heard about any base isolation implementation project in North Africa? I think you're from Egypt, and maybe, for example, in Egypt or in other countries. What's the situation on North Africa implementation of base isolation? Is this still a very new technology that we are not implementing yet?
Yes, it is very new. Last year, I got an inquiry from Egypt for a bridge in South Egypt, in Aswan. It was just a preliminary and feasibility study, and the engineers were still learning there about the technology. They were checking with Japan, with Europe, and with the US. Algeria, I have seen also one inquiry for one of the bridges recently, but it's still very, very new in North Africa or in the Middle East. In Turkey, of course, hundreds and hundreds of projects, because they have earthquakes every day, and they have also manufacturers there.
Yeah, I think that's very good. Thank you very much, Dr. Mohammed. Thank you very much for your contribution, and so very exciting webinar. I think we have to. This one of the reasons we are trying to have this kind of monthly webinars to work, to do a preparedness work on and teach what is being done in earthquake hazard mitigation. And of course, base isolation is a key solution to keep our building infrastructure after earthquakes. So with that said, I would like to thank you very much, Barakallahu Fik, for the very graceful and very interesting presentation. And we also thank all our audience who attended our webinar today and for all the questions. I would like to remind you that we are holding monthly webinars. So next month, inshallah, we will have another webinar. But next month, we are more dealing about social aspect of earthquake hazard mitigation, where we are inviting some experts to discuss regulations and emergency response on earthquakes in Algeria. So stay in touch in our page with INAS, International Network of Algerian Scientists. And we are looking forward to see you again. And thanks again for our guest keynote speaker this month. Thank you very much for your attendance.
Thank you.